Welcome back. We've talked about SGD. We talked about some variations of SGD, notably how we can ensure those variations achieve high confidence guarantees. In this lecture, I want to talk about another variations of the stochastic gradient descent. And that's basically when we want to use this method, but we don't have access to the gradient information. Let's remember our setup. So typically, we aim to minimize the average loss over the training data. Okay, so this is essentially the type of the optimization problems we are interested in. Okay, and a natural stochastic gradient that we talked about works as follows: we sample a mini batch of samples in each iteration at random, so with or without replacement, or use more advanced techniques. A couple of them we talked about in one of our previous lectures, focusing on the loss value or the gradient value. Nonetheless, what we do, we select some samples, we calculate their stochastic gradient, and then we take the average. And we use this as our update vector, essentially a good estimator of the true gradient. Okay? And that's basically the mini batch SGD method we've talked about in the course. However, there are some settings where we may not be able to, or actually we don't want to, calculate these stochastic gradients. Okay, so here I'm going to talk about three cases that this is the case. One case is related to online reinforcement learning. Another one is adversarial attack, and finally, let's talk about an example when we want to use these kind of ideas to fine-tune large language models. Okay, so we've talked about reinforcement learning a few times in the course. Obviously, that's not our major focus, but reinforcement learning is basically a formalism to talk about decision-making under uncertainty. So sequential decision-making under uncertainty. So very simply, let's say you have an agent who's interacting with an environment. Okay, so that basically means that the agent takes actions. Okay, and based on the actions, the agent may move around, let's say, in the environment. So there's going to be a change in the state of the agent. Okay, and also the agent is going to receive some signal from the environment. And typically the signal means whether the action that the agent is taking is good or bad. And the idea is that the agent wants to use these signals to improve its policy. So make sure that the actions taken by the agent in every state is as good as possible. Okay. Now, what's the catch? The catch is that we cannot observe this signal I mentioned fully in many scenarios, especially online reinforcement learning scenarios. Okay, so the idea is that the agent only gets to see the scalar reward. That is to say that it only observes the reward for the action that is played. Let's say that the agent has access to 4 alternatives, right? Whether to go left, right, forward, or backward, right? So the agent can only take one of these actions. Let's say the agent decides to go to left, and then it gets a reward for this specific action to go left. So it doesn't know how it would have performed, especially in the online cases, if the agent would go forward, backward, or right. Okay? So basically, we have only some partial observation of this signal, of this crucial information. Okay? Now, one way to talk about this mathematically, very simple, is to show that the task can be reduced to an online optimization problem. So that means that we have a sequence of optimization problems to solve over time, where there is a structure here. And the structure is that the payoff functions, okay, are linear. So essentially, they have a form like this, where W is our policy. Again, is our decision variable, it is our policy, and R is the reward vector. So essentially, in the example that I gave, R is going to be a 4-dimensional vector. First coordinate, the reward of going left, second coordinate going right, third and fourth going forward and backward. Okay. Now, in this case, if we want to perform this optimization, so one method is to use gradient descent. In this case, gradient ascent, because we want to, let's say, maximize the reward. So we need a gradient. So it's a linear function. The gradient is nothing but r. Okay. So if we knew the gradient, we could use something like gradient descent or a stochastic gradient descent to solve this problem. But as I mentioned, the agent only gets to see the reward for the action that was chosen. Essentially, if I have, let's say, again, a 4-dimensional vector, I only see one of the coordinates. So I don't know what the other coordinates are. So therefore, I'm not going to be able to calculate the gradient. Another example is adversarial attacks. Okay, so the idea is that we want to understand how adversaries can perform malicious activities, especially when we are relying on data-driven approaches and approaches based on deep learning for automating decision-making processes. Okay. So we want to develop an understanding and hopefully leverage that understanding to come up with defense mechanisms. Okay? So it is very important to talk about adversarial attacks or different kind of attacks. Okay? So what is adversarial attack? The simple example is as follows. Let's say you have a deep learning model that you want to train to perform classification. Okay? Now, the goal of the attacker is to make sure the model is not able to classify images correctly. Okay. For instance, let's say you have trained a model such that it is able to classify pandas very effectively, right? So one thing that the attacker could do is to just perturb the image with some random noise. Okay. And we've observed that if the model is not trained carefully, it could actually end up misclassifying, let's say, the image. Okay, so in this case, before perturbation, the model was able to classify this image as panda, therefore correctly with some confidence. But after adding the noise, it is classified incorrectly with very high confidence. Okay, so this is terrible. Okay. This is an example of a random perturbation where a model that is not trained well is going to perform very poorly. Okay? But you can also come up with this perturbation not in a random way, but in an adversarial way. Okay? So meaning that you come up with an optimization problem to find the worst possible noise to use to perturb the image. Okay? And this has been used in some contexts before. To basically generate what I refer to as adversarial turtle. So they've used some ideas that I'm going to talk about in a moment, in addition to 3D printing, to come up with a turtle, such that when you show it to let's say a camera that is linked to a deep learning model, is not going to be able to classify the turtle as turtle at all. Okay, so here I'm showing some examples, and in all of these examples, the turtle is misclassified. Okay, so in most of them is actually classified as a rifle, and in this specific example, it is classified as something else. Okay, but not turtle. Okay, so a little bit more mathematically, let's see what is a simple problem that the adversary aims to solve. Okay, so the adversary, let's say, only has access to some images and the return prediction of a model. So the adversary can interact with the model and has access to some images. But the adversary, it is crucial that it doesn't know what the model is, right? Or what's the architecture, what are the parameters. It doesn't know anything about that. So what's the goal of the adversary? Let yi be, for instance, the label of the image xi. So it wants to, again, make sure the model performs classification incorrectly. So it wants to minimize the score, the prediction score of this specific image. So that means that if, sorry, this has to be x, so xi. So if I perturb my image slightly, the model is not gonna be able to predict the true label anymore. Okay, so this is the meaning of the first term. And obviously, if the perturbation is large, nothing is gonna, no model is gonna perform. But the catch is that the detection is gonna be easier for the defender. So the adversary is gonna find a very small perturbation to perform this task. Therefore, it's going to add some regularization term, so to balance how large the noise is and how effective the attack is. Okay, so essentially, it wants to control the amount of perturbation added to the image, while at the same time finding the worst perturbation. Okay, as I mentioned, the adversary doesn't know the weights of the deep learning model, so it doesn't know W star. So in particular, it cannot use gradient-based methods like SGD to solve this problem. Because to solve this problem using SGD or gradient descent, we need to know this gradient. And obviously, we cannot calculate that because we don't know what W star is. All right, so let's talk about the last example, and that's related to somewhat an emerging application of deep learning, and that's large language models, and in particular, fine-tuning of large language models. Okay, so what will happen is that we have these big models that you may have interacted with, such as ChatGPT, Cloud, etc. So these are all examples of the LLMs. So there's a pre-training process which is very computationally expensive, and it involves fitting the model on very large unlabeled corpuses of data. Okay. Once that's done, we typically have another step that's called the fine-tuning step, which tends to be cheaper. So the idea is that after the pre-training, you have access to a very powerful model, but many times your goal is specific. So you want to fine-tune the model such that it performs very well on your specific task. For instance, all you care about is to code very well in Python, right? So therefore, you may want to do a fine-tuning to such that the model can help you code better, right? So, or maybe your goal is to, again, prove convergence of optimization algorithms. So you may want to fine-tune the model, these LLMs on, let's say, optimization books, right? That would help you to be more effective in solving your mathematical problems. Okay, and this step is slightly cheaper and relies on a smaller, let's say, data sets. Okay. However, we've observed that these LLMs tend to perform very well as their size grow. Okay. On the other hand, because the size is growing, there's going to be a substantial memory overhead needed when performing gradient computation in the fine-tuning step. Okay, and the premise is that this is very crucial to address, especially for applications that we want to perform this fine-tuning on device. Okay, so I have my own personal computer or laptop, and let's say, given privacy reasons, I want to perform this fine-tuning locally. Okay, so obviously I'm not going to have access to a lot of computations nor memory. So the fine-tuning step that I do has to be made very, very efficient. Okay, so it turns out, as I mentioned here, the gradient computation is very, very costly. However, there are ways, based on what we're going to talk about in this lecture, to make this process a lot more efficient, and that relies on not calculating the gradient and using something else that we're going to talk about in a moment. Okay. So there you go. So this is like a short motivation for this lecture. There are scenarios where we cannot have access to the gradient, or like the third example, we don't want to calculate the gradient due to memory requirement or limited computation. In the next video, we're going to talk about a simple idea on how to do this. Essentially, how to alter or modify SGD such that we can still use it without access to the gradient information. I'll see you next time.